So this is the second part of talking about the gradient. So far this is a little bit of review right here. We've seen gradients of functions of x and y. Today we're going to look at functions of x, y, and z. So we'll recall some gradient properties from before. So if I have a differentiable function with partial derivatives f sub x, f sub y, the gradient with this Greek letter del upside down triangle is a vector given by the gradient of f equals the partial with respect to x in the I direction, partial with respect to y in the j direction. And at a point p naught, the value is just given by evaluating each of those at that point. And so what we had as far as properties go is that the gradient gives the direction of greatest increase in f, that's the steepest ascent. The negative of the gradient gives the direction of the greatest decrease, so that's the steepest descent. Also, the gradient at a point is normal or orthogonal or perpendicular, all those mean right angles, to the contour through x naught, y naught. So those were all properties from before. Alright. We also had all of our derivative properties. The gradient of constant is 0, linearity property, product rule, quotient rule, all those. So we talked about those last time, so I'm not going to go through those again. But if I need a compute a gradient, I can use all the really all the derivative properties that I have from before. And we can also compute a directional derivative using the gradient. So if I need to compute a directional derivative, I can use the gradient and the dot product of that with the unit vector of the direction I'm heading in. So that's just partial with respect to x times the I component of the unit vector, partial with respect to y times the j component of that unit vector. Alright, what we're going to get next is sort of the same thing here. So this is going to be a gradient of a function of x, y, and z. So rather than say z is x squared plus y squared, this would be something like x squared plus y squared plus z squared equals 3, or something along those lines. Alright, so properties are going to be similar to those that we just saw, though. So let f be a differentiable function with partial derivatives f sub x, f sub y, and f sub z. So now we get also this z component. Then the gradient of f, denoted by the same value, this del f, is a vector with the partial with respect to x in the I direction, with respect to y in the j direction, and with respect to z in the k direction. At a particular point, x naught, y naught, z naught, the value of the gradient is given just by plugging the coordinates in for each of those components. So if we need to plug in values, we can plug in values to get a specific gradient at a specific point. Alright, similar to before, this gradient at a point gives the direction of greatest increase, and the opposite, this negative gradient, gives the direction of the greatest decrease. Also, this gradient is normal or orthogonal to the level surface through x naught, y naught, z naught. So rather than being normal to a level curve, now we're going to be normal to a level surface. And that's going to be a key component that we can use to find tangent planes and things like that. Alright, same properties apply as before. All these derivative properties are exactly the same. Derivative of a constant is 0. Gradient of a constant is 0. Derivative is linear, so is the gradient. Product rule, quotient rule, all those exactly the same. Even in 3 dimensions. And then the same thing as before. The derivative, or the directional derivative in a unit vector, so that u has to be a unit vector. The directional derivative in the direction of that unit vector is given with the dot product with the gradient. So gradient at that point times a unit vector heading off in whatever direction we need it to go. Alright, and again, that's partial with respect to x times the I component of the unit vector, partial with respect to y times the j component of the unit vector, partial with respect to z times the k component of that unit vector. So everything's the same as before, only now we have 3 dimensions rather than 2. Alright, so here's a couple of things. If we have a tangent plane and normal lines, Uh, so a tangent plane to the surface, we've already investigated that a little bit for two-dimensional surfaces. If I have z equals some function of x and y, where z can be written explicitly in terms of x and y. But suppose I can't do that. Then how do I find a tangent plane? Well, this normal vector n, okay, can be found using the gradient. So here's just sort of a basic definition here. Suppose a surface S has a non-zero normal vector n at the point P naught. Then the line that's parallel to this normal vector, that's called the normal line to S at P naught. And the plane that's through P naught with normal vector n is the tangent plane. So the normal line, that's just the line perpendicular at our point. Tangent plane, that's the plane that's going to approximate our surface at that point. And so here's sort of an example of that. Here I have a curve right here, has some sines and cosines, things like that involved. But as I move this guy, I can see the tangent plane is changing. I can also see right there this normal vector, so that normal vector right there, I can also see. A normal line would go straight through there, straight through that point. So anywhere on here I can find any sort of normal planes. We'll go ahead and bring this up here. So this would be sort of a horizontal tangent plane with the normal line coming right through there. But any place that we look on our surface, that's always going to be tangent. So same concept as tangent that we had before. This normal line directly perpendicular to the surface. Also, this normal vector that we have right there is also the same vector that we use to get our tangent plane. So all of those are related. Alright, let's go to the next one. So here's a few examples for finding tangent planes, things like that. So find a unit vector that is normal to the surface, x to the fourth plus y to the fourth plus z to the fourth equals 3 at the point 1, negative 1, negative 1, and give the standard form equation of the tangent plane at that point. Alright, so for this one, really we just need the gradient to be able to find the normal vector. So a unit vector normal to the surface, we can get the normal with the gradient, but then the unit, we'll have to unitize it by dividing by its length. So we'll do that part first. So here's my surface. We'll go ahead and show this again at the end, but this is that surface x to the fourth plus y to the fourth plus z to the fourth equals 3. And I see there's my tangent plane right there. So we'll see how to get the exact tangent plane and then take a look at that again at the end. So let me click this one. So the normal vectors using the gradient for some function f of x, y, and z equals c. Then plugging the point values in. Alright, so for this one, our f of x, y, and z is just this left-hand portion of our equation right here. So the x to the fourth, y to the fourth, z to the fourth, that's our function f. So if we take partials, partial with respect to x, okay, this one's a pretty easy one. That's just 4x cubed. With respect to y, 4y cubed. With respect to z, 4z cubed. So there's all my partials. So there's my gradient vector. 4x cubed, 4y cubed, 4z cubed. And at the point P naught, which in this case is 1, negative 1, negative 1, our gradient's going to be 4 times 1 cubed, 4 times negative 1 cubed, 4 times negative 1 cubed again. So 4, negative 4, negative 4. So there's our gradient vector. That will also be the normal to the surface at that point, but we're going to want a unit vector. I keep clicking the wrong arrow. Alright, so for a unit vector, we go ahead and divide by the length. So the length, 4 squared, and 4 squared gives me 48. So we're going to divide by 4 square roots of 3. Alright, so 4, negative 4, negative 4, divide by 4 square roots of 3. We get 1 over root 3, negative 1 over root 3, and negative 1 over root 3. So there's my unit vector. Okay, so now it's a unit vector normal to this surface. Alright, we also want the tangent plane at this point. So the tangent plane at this point, I can go ahead and get that by using my standard form of a plane. So remember when we were talking about a plane, we always had this vector that we're going in the direction of. We could use this unit vector or even this one before we got it unitized. So this one's going to be this partial with respect to x, with respect to y, with respect to z at the point, times the x minus x naught, y minus y naught, z minus z naught equals 0. So there's our point normal form. So I can go ahead and plug in the values that I got from my partials, 4, negative 4, negative 4, plug in my points, 1, negative 1, which becomes plus 1, another negative 1 becomes plus 1, and then I just simplify. Alright, so this is 4x minus 4 minus 4y minus another 4 minus 4z minus another 4 equals 0. So we get 4x minus 4y minus 4z, and then all these minus 4's add up to a negative 12. So this is the standard form of that plane right there. So the tangent plane at 1, negative 1, negative 1. If I divide through by 4, I can get x minus y minus z minus 3 equals 0. Alright, so that's my tangent plane right there. You could use this. It's just easier to divide everything by 4. It gives me a little bit simpler equation. Alright, so here's my unit vector that's going to be normal to the surface, and there's my tangent plane. So again, on this guy, here's the graph. Notice this is my point. So in the x direction, I'm coming out 1 unit. The y, I'm going back negative 1 unit back here, and then the z, that's also a negative 1 unit right there. So 0 is actually up here, and then negative 1 would be right there. So there's my point, and there's my tangent plane. X minus y minus z minus 3 equals 0. Alright, so we can see that's right on the corner of this surface right there. Alright, we got 2 more examples here. First one, or the second one here, example 2, find a unit vector that is normal to the surface. Natural log of x minus y over y plus z equals x minus z at the point 1, 0, 1. Alright, so again, something that's normal to this surface and the standard form equation of the tangent plane at that point. Alright, so we'll go ahead and try with this one. See what we get. So this, again, we have to have this f of x, y, and z equals a constant to get started. So I'll go ahead and move everything over and make this natural log minus x plus z equals 0. So you need a constant on the right to be able to look at this level surface to this function f. Alright, so this is going to be natural log of x minus y over y plus z, all in the natural log, minus x plus z. Now we can go ahead and do partials. So partials are going to be a little bit tricky on this one. So this is a little bit harder than the last one just because of the partial derivatives. So on this one, remember, natural log will get 1 over this value on the inside. So derivative natural log 1 over this, which I can also think of as reciprocal. So notice all of these have a y plus z over x minus y, and all of those, times the derivative of the inside. So a derivative of the inside is going to change. With respect to x, I'm just going to get derivative of the top 1 times the bottom y plus z minus the top times derivative of the bottom. There's no x's, so that's a 0. And then divided by that denominator squared. Okay. We also have an x out here, so I also get this minus 1 on the outside there. So we got the inside of the log flipped for the reciprocal, quotient rule for the derivative of the inside, and then minus the 1 on the outside. Simplify a little bit. So this top just simplifies to y plus z. We got y plus z times 0, or minus 0. So that y plus z divides with one of these y plus z's. The other one down here divides with the numerator up here. So we got 2 of these y plus z's that divide out. So we just get 1 over this x minus y minus 1. Okay. Eventually I'm going to plug in a point. So I'll just leave it like that. I'm not going to combine those fractions or anything until I actually plug the point in. So we'll leave that as is for now. The other one here, the partial with respect to y, again I get flip the inside times the derivative of the inside of this natural log. So derivative with respect to y is going to be derivative of the top negative 1 times the bottom minus the top x minus y times derivative of the bottom with respect to y now gives us a 1. Alright. No y's out here, so we're not going to get anything there, but we do get divided by that denominator squared. Simplifying this, I'm going to have y plus z divide out with this y plus z, so that's going to divide out, so I only get one of those down there. X minus y I'll also keep, and this simplifies to negative y minus z minus x and then plus y. So that's what I get on the top, and negative y plus y, those subtract out, so we just get negative z minus x. Again, I'm going to leave that as it is. I really can't simplify it anymore, but we'll plug in that point in a second. Alright, last partial here. Flip the inside again, and then partial of this part with respect to z. So, derivative of the top is 0 times the bottom, minus the top times derivative of the bottom, which is 1. Alright, so that's what we get on the top there, and then divide by denominator squared. So quotient rule for all those. On the outside of this natural log, I also have a z, so that's where I get this plus 1. Alright, so 1 over this gives me that fraction. Derivative of the inside, I need a quotient rule, and then plus the 1 on the outside. This will simplify again. This is 0. We have one of the y plus z's that divides out. And then this x minus y will divide with this x minus y and leave me with just that negative 1. So we get negative 1 over y plus z plus 1. Alright, once I've got those derivatives, that's really the hard part of this problem, is computing all those derivatives. So once I have those, now I can go ahead and plug in some numbers. So when I plug in our point where x is 1, y is 0, z is 1, I'll just get 1 over 1 minus 0, minus a 1, so 1 minus 1 is 0. Negative 1 minus 1 over 1 times 1 gives me negative 2. And negative 1 over 1 is negative 1. Add a 1 again, 0. Alright, so for this particular equation, this means that my gradient is just going to be no i's, minus 2 in the j direction, and then no k's. So just negative 2j. So there's my gradient. Same thing as the directional normal vector. So this normal vector in the direction of this u is going to be negative 2j. Alright. So a unit vector that's normal to the surface, we actually need to divide by that too. So the unit vector in this case, I'll go ahead and put it right in here. Alright, so the unit vector is going to equal just this j component right there. So, and same direction, we want to keep that negative out front. So we can't ignore the negative, but that whole thing should just be a negative j. Alright, so anything that we get, we're going to get the same thing as this guy over here. Actually, I like my negatives wide, so we'll put that in, just erase the 2. Alright, so there's my unit vector negative j that I get. The tangent plane, this is going to be 1 unit in the j direction toward the negative side. So the tangent plane is going to be parallel to this xz axis through our y coordinate. So if the only part I'm getting is this j that's normal, that means that it's coming right out of this xz axis in the y direction. And all we're going to get is just y equals whatever our y coordinate is. In this case, we're going through the point 1, 0, 1. Y coordinate is 0. And so tangent plane in this case, y equals 0. Now we have that unit vector, we have that tangent plane, y equals 0. I'll go ahead and show you the surface that's kind of broken because we do have some undefined values due to this natural log. So I'll show it to you, but it doesn't look as nice as the last one. So here's our surface here, and notice I do have these broken values. There are regions where I'm not defined, but there's my y equals 0 plane. And that's going to be normal right at this point right here. So notice right at that point, that's where I'm at this 1, 0, 1. So 1 in the x direction, 1 in the y, or 0 in the y, 1 in the z. But this guy, so there's the 1 in the x, 0 in the y. I'm still on that y-axis there, or the x-axis, 0 in the y direction. and then up 1 for my z. So that's 0, up 1, z. So that's this point right here. Notice that is going to be tangent right at that point right there. So looks like that's actually a saddle point right in there. Alright, so that's that surface right there. Alright, last one here. Find the direction from P naught for 1e negative 1, or point P naught, in which the function f of x, y, and z is z natural log of y over x increases most rapidly. Compute the magnitude of the greatest rate of increase. So with this one right here, the direction of the greatest rate of increase, that direction is given by the gradient. So we just need to find the gradient and its magnitude for this problem. So compute our partials to get the gradient. So this is, for this particular function, partial with respect to x. So z is a constant in our case, so we just have that z times derivative of this guy. So derivative of natural log y over x is going to be 1 over the y over x, so that's x over y, times derivative of the inside. So derivative of the inside, that's going to be just negative y over x squared. So you can think of that as y times x to the negative 1, which would give me negative y x to the negative 2, or negative y over x squared. So you can change that to a power and do it that way if you want. This is what you should get. You can also use quotient rule if you like. That will give you the same thing. Once I have that, notice y's are going to divide out, x's are going to divide out. Still have one x in the denominator, but instead of x, y, and z, now it's just negative z over x. Alright, so y's divide out, 1x divides out, and we get negative z over x. For our partial with respect to y, this is going to be similar. Z out front, since it's a constant, times this x over y, flip inside the natural log, times derivative of the inside. And derivative of the inside is just going to be this 1 over x. So since y is our variable, we have 1 over x times the y. That's the derivative, 1 over x. X's divide out. We just get z over y. So there's our z over y. The last partial with respect to z, is even easier. Natural log of y over x, that whole thing is constant. So just a constant times z. Derivative is the constant, natural log of y over x. So that's it for that one. Alright, now with those partials, I'm going to go ahead and plug in my point. So when we're at 1e negative 1, so we're going to get negative 1 over 1 for our z and x, negative 1 and e for our z and our y, and then e and 1 for our y and our x. So negative of negative 1 over 1, that's just 1. Z over y, negative 1 over e. I'll just keep that negative 1 over e. And then the natural log of e turns out to be 1. Alright, so there's my partials evaluated. So we got 1, negative 1 over e, 1. That's the direction of the greatest increase. The magnitude, that's going to be the square root of those guys right there. So square root of squares, so we got 1 squared plus 1 squared plus that 1 over e squared. I'll just leave that as 2 plus 1 over e squared. If you need a decimal, it's about 1.461 if you want to compute that decimal. But there's the direction of greatest increase, and the magnitude about 1.46. So that's it. So anytime I'm looking for that sort of thing, I just need to find the gradient, and that just means partial derivatives all over the place.